So first seminar in the second semester, and we are happy to have Nikita Markarian from the University of Strasbourg, multiplicative convolution and double shuffle relations. Nikita, please.
Thank you very much for the invitation. I'm happy to be first in the series. Spring series of seminars. Okay, so let me start with beginning. So I'll start with the homological equation, which is classical thing. I want to define a Greenfield associated. So we have this differential equation where on affine line, so we have a connection with two singular points, and so it has residues x0 and x1, and x0 and x1 are just formal letters. So you can think about real matrices, but you can think about just algebra, free algebra generated by x0 and x1, and completed with respect to completion. And then we have a universal solution of this equation, such that, so we have two solutions, in fact, this G0, which is written here, so it has this asymptotics, and another one which has this asymptotic near 1. It has asymptotic near 0, near 1, and the ratio of them is called the Newton-Logic of Greenfield associate. So it must be thought as a holonomy of this connection from a point which is infinitely close to 0 to a point which is infinitely close to 1. Unfortunately, yeah, I mean it's not well defined because it's some divergence. But we can write down a formula, this formula. So we can define the coefficients. Let's call them. They're called multiple zeta values. There's coefficients of this associated like this, and
so it's a formal expression, yeah.
Yeah, it's formal expression. It's an element of Newton's homologic of thing is an element of completed free algebra generated by x0, x1, and
x0, x1 are not commuting.
Yeah. It's free algebra. Exactly. Yes, and if just formally integrating, we can write down this integral so that these numbers are certain integrals like this iterated integral, and there are some problems with divergence. So sometimes the integrals diverges, but then there is this method of Lie-Murakami, which allows us to write down all coefficients of Newton's homological equation. But I don't want to stop at this.
Yeah, so the x1, the power of x1 is always 1 in the summation, right?
Sorry?
The power of x1 is always 1.
Yes. It's more than 1. Yes.
Well, x1 has
x1
power of exactly 1, right? x0 you have x
it's sounds strange. No, it shouldn't be like this. No, yeah. Thank you. I think yes. No, it shouldn't be. No, sorry. Yeah. I think it's not true. Yes, I think it's some misprint, but I can't fix it right now. Thank you very much for this. No, it's
fine. That's fine. Go ahead.
Yeah. But yeah, you can find formula in any. Yeah. Anyway, thank you very much. Okay. Yeah. So this is but what's important for us that it's not just numbers. It's a periods of some integrals. So. Or you can think about motivic zeta values, it represents some Tate motifs, or yeah. Anyway, so what is important? Okay. So there is we can present multiple zeta values in terms of number series this way. So it's the fact that it may be just by direct calculation of these integrals, iterated integrals, and the product of two multiple zeta values is again combination of a multiple zeta value. The simplest example is like this: we multiply zeta of 2 by zeta of 2, and just multiply this series, and then we can rearrange them in this way. So have three summands here, and we get this result. And more generally, one can define product of two here, K and L bold. They means that it's a sequence of numbers. So we can define for any multiple zeta values the product on the right hand side. It will be sum of the sum. So this thing means the sum by some so-called shuffle. It's reminds shuffle combination of this K and L. So there is some rule. I don't want to emphasize this here, but the point is that exactly in this way, rearranging terms, one can write down this relation. In fact, this relation not only in multiple zeta values, but it's relation on polylogarithmic functions. So the polylogarithmic function is a solution of our cosmological equation, and multiple zeta values its value of this function at 1. So in fact, these Staffel relations, which is called Staffel relations, they're not for just numbers, but for these functions. But it's not so important. So there are Staffel relations, these ones. There is another set of relations called Schaff relations. It essentially says that the cosmological derivative associated is group-like element, and that follows immediately from Fubini theorem for iterated integrals. So these relations, and the most mysterious part is regularization, because we have this relation and these relations, and we can consider the indexes such that the zeta values are not defined, but some combination of them are defined, and this gives us some additional relations between multiple zeta values. And this three combination, this three set of relations is called a regularized double Schaffer relation. So it was introduced by Ihara Kaneka Zagier in 80s, and everything was is defined. And the conjecture of they stated it's that it's all geometric or motivic relations between multiple zeta values. Pardon, it's C, must be Z. Okay. Yeah, this is the conjecture, and this is one of my motivation of this story. So it's a rather intriguing conjecture. Okay, so then.
And by the way, what's the status of this conjecture? Because it's quite old.
Yeah. No, it's still there. I will discuss it at the end of this talk.
Okay.
No, but yeah. So in late 90s, I think, Georges Lassagne in his thesis he formulated these relations, double Schaff relations, in some beautiful form. It says that it's some element of some Hopf algebra is group-like. So it's a rather mysterious calculation, but it's nothing just this calculation with series we discuss here, but just packed in some nice form. So it looks less here. So there is algebra with free generator y1, y1, y2, and so on. And in fact, this is these y's are just elements of our algebra generated by 2. Sorry, it's 0, x2. Yeah, x0, x1, and this must be 0. Sorry, and yeah. So this is a subalgebra of this free algebra, and then we define coproduct on this algebra this way. Then we can present our Greenfield associator, which is essentially symmetric with respect to x0, x1, and more or less. That's why, yeah. So we present it in this way. So we present this component which lies in right ideal generated by x0 and right ideal generated by x1. Then we take only part this, so we exclude this part. We get this thing, and then we should modify it in this way, where gamma of y1 is something which depends on the associator as well. In fact, this is gamma function. It's called gamma factor. So then we have this expression, mysterious, and the result that regularized double shaft relations means that this thing is group-like with respect to this coproduct. This was the statement of the Rassina thesis. Is very nice statement, but and then in 2006 it was a report of Terrasoma at the ICM, where he described some project which gives geometric meaning to this formula. So my work is was attempt to understand this geometric approach. Unfortunately, it was never published. In the Delin Terrasoma, there is a letter of Delin to Rassine, and there is unfinished preprint which contains some text, but it's really hard to understand what's going on there. But my attempt was to understand it. I need to mention here Enriquez and Furusha approach, where they developed these things in great details, but their approach is very algebraic. And for me, I would like to understand the geometry which lies behind this. And this, yeah, so this is what I'm going to talk to you about. So as far as I understand the idea of the linear Terrasoma is the following, that we have the group-like element. But there is some Tanakian formalism which says that group-like element in the Hopf algebra is the same thing. If you see a Hopf algebra group-like element, you need to find the Tanakian category and automorphism of a fiber function. It's essentially the same thing. So what is this in this case? What is the category and what is automorphism? And the Terrasoma answers that category is some category of previous sheaf I'm going to describe. Tensor product is given by convolution, and fiber functor are binary cycles. I don't know how to see it from. I mean, how to understand that this story is connected with previous sheaves and financial cycles. Maybe it's possible if somebody can tell me, I will be happy. But yeah, I don't know. Okay, so yeah, another thing is was the motivation of the Delin in Terrasoma. As far as I understand, it was to prove that double shaft relations are implied by associated relations, and that's what I'm going to explain. What is associated relations? So in fact, this associator must be thought not as an element of fundamental group, pluripotent, but of a fine line without 3 points, but as a path from 0 to 1. So I think, as far as I understand, the idea is that we have some path which is a straight path, and we have another path. It's not a real path. It's an element of pluripotent completion, which is called Durham and Betty, and this associator, it measures the difference between them. So this is the as far as I understand, it's in Greenfield, and it goes to Eskizdan program the Grothendieck, where he described the motivic group or Galois group of Q bar in terms of its action on a fundamental groupoid on modular space M0n. And the point is that we can look at fundamental groupoid of M04 and look at this path and consider how our group acts on this. And this action should be compatible with other. So we have M05, for example, and we have projections, and it must be compatible with this action. So we have action on M05 as well, and the conjecture of Grothendieck that essentially it defines the whole action, as far as I understand. But yeah, some very theoretical thing. But the point is that if you have in a nutshell, it gives a relation on associator, which is called pentagon equation, and it corresponds to that we have in M05. So it's I draw here M05 real points, which is the circles, and in this circle we have a pentagon, which is this path, and it is constructible in M05. So any path is in fact this. It's not the straight line, but we can correct them by this term, and this gives this equation on associator. And yeah, so there's a pentagon equation, and it gives some relations on coefficients of associator. And this is called associator relation between MZVs.
But categorically, these variables xij, they are what?
No, what do you mean category? Xij is this is elements of group ring of M05. It's logarithm. So this thing lives in the group algebra
unipot
completion,
yeah, okay.
Of group algebra fundamental group on M05, and Xij they are corresponding elements also. So
okay.
Yeah, so it's a rather complicated equation, and it's not even easy to see how to write down relations between MZVs that it gives. In fact, yeah. So, but anyway, this is pentagon equation, and many people believe that this is the strongest set of equations. So, it's essentially this is the idea of Grothendieck, more or less. That all relations between MZVs are given by pentagon equation. In particular, it means that they imply the double Sheff relations. So yes, and to prove this statement was, as far as I understand, the initial motivation of Glenin-Tarasova, but since then this was proved in many ways, and Fruscio, Enriquez Fruscio as well, and many others, and Fruscio without Enriquez. So a lot of proofs with this statement, which is, yeah, if you believe that it's the strongest one, so it's not surprising that it's true. But the opposite. So, but if
so I have a quick question here. The pentagon relation. So it looks like this is something like a Greenfield's associator. So the X1 Xij here is the Xij and the Xji actually will be the same from this setting.
Yeah, sure.
Okay.
Yeah, maybe up to sign, maybe.
Oh, up to a sign or without sign?
I don't know. I don't remember.
Okay.
Yeah. Anyway, so yeah. So if conjecture of Ihara, Kaneka, Zagier is true, then they should be equivalent, and it should imply this direction. So, but it's not absolutely clear. So this direction is more or less clear, yes, and yes, it's proved, but this direction is. So we can reformulate conjecture of Ihara, Kaneka, Zagier in this question: does a regular double Sheff relation implies associated relations? And now this question has nothing to do with any number theory or whatever. It's just we have two sets of algebraic relations, and the question is are they equivalent or not? Okay. So now I'm going to discuss what was this perverse sheaves, vanishing cycles. So okay, so our category will be the category of perverse sheaves on GM, which is multiplicative group. So this projective line without zero and infinity, which has no singularity outside one. So it is the only singular point possible is one. Then we can define vanishing cycles of. So we can, yeah, so we need to specify direction, but I can't specify like this direction. But for us, it will the helpful definition is given by these three authors. I'm afraid that I'm not sure how to pronounce them. Caligo, Granger, and Maisonneuve. This is a paper of 80s where they identify, they give this definition of vanishing cycles. So we have this interval from 0 to 1, and we consider the cohomology will support this interval. In fact, this is if so f is a shifted local system outside 0, 1, and infinity. So in fact, this is first cohomology, but it's because it's shifted. So and the nearby cycles are given by this analogous formula, and this is used a lot by Kapranov and Shachman in the work about perverse sheaves and configuration of lines and so on. It's a series of papers where this formalism is used a lot. So I recommend the paper to this definition. So in particular, if you start to stratify your semi-interval by like semi-interval and this is stratification, which is semi-interval and this point 1, it gives you a cone, and the corresponding exact sequence is this so-called Milnor triangle, and this map is the variation map from vanishing cycles to nearby cycles, and nearby cycles they're just fiber at a point which is infinitely close to 1, and vanished cycle is maybe defined as, if you wish, as this cone. So for technical reason, it's useful to consider only such sheaves which have where this thing vanished, and it means that var is now in inclusion, and yeah. So the basic example is just we extension of a shifted line, shifted vector, shifted local system outside 3 points by star at 1. So this is you can restrict yourself only thinking about only this kind of perverse sheaves. So we have in fact local system and extend by asterisk. This is the classical result. Also, firstly, I think appeared in this text that if you have a disk and you have a perverse sheaves on it with singularity at 0, then it's this thing is totally described by vanishing cycle, nearby cycles, and var and can between them, and we have this relation where T is monodromy around 0.
Is it Macpherson-Villanen?
Yeah, it's also Macpherson. Yeah, but it's also paper how to glue perverse sheaves. Yeah, it's classical result, and this three yeah, and Macpherson-Villanen also uses this formalism.
Yeah, it's more or less the same primary.
Yeah. By the way, in some books, there's another order I found that T minus 1. I don't know what is better, but I think it's not. Yeah, I'm not sure. Okay, so yeah, and Kapranov Shachman. So you can rephrase it in this way that this category of perverse sheaves is like it's a diagram with two vector spaces, 2 arrows, such that this composition is 1 minus invertible operator. So it's an equivalence of categories. Okay. Oh, sorry. Yeah. By the way, in the preprint of the Linterasoma, this is taken as a definition of perversive, which makes everything nightmare because if you take this as a definition, then you're trying to work to make some operation. It's really hard to understand what's going on there. Okay, so yeah, so now I want to say about transport algebra. That's was important thing in a recent talk of Mish Kapranov on about the surgeons and perversives. So I want to say what it is in our case. So on nearby cycle is just it's just a fiber of our sheaf at infinite point. So it's acted by fundamental group because any fiber we have, you can take the monodromy, have the action of monodromy. So we have a loop. You can take holonomy around loop and this action of fundamental group on the fiber. And what does act on vanishing cycles? So the idea is that we take vanishing cycle, we apply var, and we're in nearby cycle, then we apply element from fundamental group, and then we apply con. So this gives action of loop A. So A is an element of fundamental group. And so this is the action of our algebra. So how the composition looks like. So we have action of A, then the action of B. If we compose there, then we need to have to compose con var, which gives us 1 minus monodromy around this point, which means so it's essentially the group algebra of pi1 of our space, but with new multiplication. And this new multiplication is called by Jacobson, I think, homotop. So it's if you have an algebra and an element, you can produce new product. So it must be alpha, sorry, which is just xy equals to x alpha y. So here's product of AB is A1 minus x1 B. So in fact, this algebra is isomorphic because it's so free. It's isomorphic to left ideal, right ideal of our algebra, and we'll add 1 because we want to have an algebra with 1. So our algebra is this. And we have another version of this algebra if we consider instead of, so there's another version of Canvar formalism where in another version of var, and such that Canvar is now not x1 minus 1, but logarithm. And in this case, we get this algebra, which exactly this algebra from definition of Rastenek formalism. So this is the first character of our story. So this is transport algebra, which acts on vanishing cycles.
So sorry, because there are topologies here. I mean, there is a topological model for that. I don't think it's special for
no, it's not special. Sorry, yeah, it's absolutely universal thing. If you have vanishing cycles, then you can produce an algebra which acts on it.
Yeah.
So sorry. Yeah, I mean, I didn't emphasize here, but yeah, it's absolutely universal story. But in our case, it will be this algebra. Yeah, thank you for the question. Yeah.
And in your transport algebra, here the alpha in this W multiplication is 1 minus x1 or something else.
Yeah, but we multiply. So we
I see. Thank you. Yes, that's alpha is 1 minus x1.
Yeah,
yes.
A new product of A, B, it will be A, y minus x1, B. So essentially, this is just this.
Yes, I got it. Yeah, that was the notation was clear now.
Sorry, yeah. Okay, so yeah. Okay, so anyway, so this algebra is just this thing. So how to prove it? But in fact, it's not proof. It's a construction of this. So this is a central character of our story. This isomorphism. the isomorphism of so we have our perverse sheaf on GM, and we give extension which extend by shrink at infinity and by star at 0. So we have yes. So in fact, I omit here. I always omit the notation of derived function. I always mean derived functors. So I think so. And the statement is that the vanishing cycles of f at 1 is isomorphic to this cohomology, and this isomorphism is a central character of our story. In particular, let us look at this isomorphism. So, for example, consider the local system outside our 3 points and continue by shrink at infinity and stars to 0 and 1. This one. Then by this isomorphic, it's isomorphic to nearby cycle at 0 and nearby cycles at 1. So it gives us this isomorphism. In particular, it means that we have isomorphism between nearby cycle at 0 and nearby cycle at 1. And this isomorphism is exactly holonomy of our local system along this straight line. It's the property of our isomorphism. So how to prove it, and better how to construct this isomorphism is the following. It's like shrinking arguments. We consider this interval. So we consider a standard triangle shaded with this closed interval embedded in our affine line, in fact, and we consider cohomology. So this is so consider this I shrink here, and here is yeah. So the point is that this thing is homeomorphic to GM, and we have our local system, which are outside these 3 points, it's local system, and it's extended by shrink to infinity and by star to this another whole, and this cohomology always 0, so they vanish. So it means that cohomology of this one, so this thing is isomorphic to cohomology of this one. In particular, if we consider it's more general statement. If we consider our definition of vanishing cycle in terms of this interval, it states that this thing shrinks to this one. So yeah, it's not only proof that these guys are isomorphic, but it gives concrete isomorphism. So yeah, this statement appears in fact, the only place where I found that it appears, it's Nicholas Scott's book, Convolution and Equidistribution, where he uses this category for some absolutely different reason, for some number theory. So yeah, sorry. Now I want to define convolution. So we have a multiplicative group, we have multiplication, and convolution is just convolution of sheaves with respect to this multiplication. And in fact, this, so we as usually they take 2 sheaves, take the external product, and then they take the push forward with respect to multiplication. In general, this is not sheaf. It's not perverse sheaf. It's a complex of perverse sheaves. That's why we need to introduce this cutting. So we just take only one zeros cohomology of this complex, and just by from Kunert formula implies that this functor is tensor, this functor, which is this functor, the cohomology of extended sheaf is tensor with respect to this convolution. It's more or less Q-unit formula, and it is. Yeah.
Is the cutting with respect to the perverse?
Yes.
Or just with a standard complex degree?
No, it's even a perverse.
With a perverse cut. Okay, thank you.
But yeah, yes, yes. In the meantime, I will mention. So in this way, we said this is the tensor functor, and we introduce isomorphism, and it makes this also equipped with this thing with tensor functor, but they're not fiber functor. So we have category with tensor product, but they're not fiber because they're not faithful. Because, for example, if a shift has no vanishing cycle, it's smooth at 1, it obviously is 0, and it's not allowed for fiber functor. That's why Deligne and Trasom introduced the third quotient. That they introduced a quotient of this category by shifts, which is in kernel of this functor, and they proved that this is this category is category of models over our transport algebra, and this is a fiber functor of this category. So this is the idea of, I think, yeah, that's why. So, and by the way, in this category, quotient category, you don't need this cutting because the convolution is again perverse shift, so it's okay. So the thing you need to cut that they are smooth in 1, as far as I understand. So it's it's a not nice category, but it's a little bit implicit because this for me. So you can define convolution in terms of projection of M05 to M04, and then this is a standard thing. You take pullbacks from, you have projections, many projections from M0, many projections corresponding to forgetting points. So you have pullbacks, and then you push forward, and then in other projections. So the standard convolution in terms. So here is the picture. So the picture is M05 over M04, and here is the singular fiber over 0. This is a singular for fiber over 1. But in fact, if you look at GM, you need to imagine that this fiber is blown down because GM times GM, it means that you have just 2 points. It's 2 points on P1 which differs from 0 and 1, but yeah, they can coincide, but this is so you need to blow down this fiber. So here on this picture presented, so this so I missed something. Sorry, I missed this thing that I can, due to this isomorphism, I can present now vanishing cycles by 1 cycle. So I think about this. I can imagine this cohomology with support as kind of cohomology with support as a homological cycle by Poincare duality, or if you wish, I don't know. So I can imagine vanishing cycles as these intervals, and with some additional structures, so some class of cohomology with support on this thing. So on this picture, I present the convolution of 2. So we have 2 vanishing cycles, and we have convolution. Convolution is this vanishing cycle are presented by intervals, and their product is presented by a square. In fact, if you imagine that this fiber is blown down, so you have this square. Yes, this 1, 2, 3, and 4. And this gray figure presents the product of this vanishing cycles, which is lives in M05, and yeah, and it presents the push forward of this of convolution, which is push forward of this, and so there are some because this is a pentagon, there are some compatibilities. So we can present for example, at over 0 we have a cycle, we have a nearby cycle which here is represented by this figure, which is tailored from 2 vanishing cycles, this interval and this interval, and this present this product of vanishing cycles. On the other hand, if you look at the fiber over 1, because this thing is blown down, it means that this thing presents also vanishing cycle. So and
so I'm a bit confused with the
yeah.
notation. Zero is what?
No,
0 on the horizontal axis.
no,
Yeah.
this horizontal thing is present M05. So it's line. It's
So 0 and 1 are just points of P1.
points on P1. Yes,
Yeah,
this
okay.
is P1 essentially, and so this picture presents this this one of this map is, and this map essentially the same thing. So I'm trying to draw the push forward. So I want to present at the beginning what it's a picture presents the convolution. So I take 2 vanishing cycles, they take external product which lives now in GM times GM, which is this one, and then they're presented by the figure, and then I take the push forward of this, so cohomology, and yeah, this picture presents this okay, so yeah, presents this map. So we have a family of curves over M04, which are non-singular out of 0 and 1, and yeah, and I think that it must be clear from this picture, and I have no words. Sorry, but I think it's not clear. So what I want, so in a nutshell, what I want to say, I want to say that there is vanishing cycle near 1 at 1, which presented by this interval, and it gives one isomorphism between vanishing cycle of convolution and product of vanishing cycles. This one, and there is another cycle at 0, which is composition of these 2 ones, and this gives another isomorphism between, and we have holonomy between these 2 cycles, and this is all things are compatible because we have this pentagonal figure. Okay, so I wanted to mention that in fact at here we have Verdier specializations of these shifts. So on, for example, on this cycle, it's when we restrict here, it's not our previous shifts, but for example, if they can come from local systems, then these guys are abelian this guy have abelian monodromy. So if you it's like it was a local system with 3 singular points, and when it goes to this singular fiber, two points they meet and have only two singular points, and it means that this is these guys have an abelian monodrome. So this gadget specialization. So yeah. Okay, so it's just looks very very formal, but okay. So what I want to do next, I want to consider another isomorphism between vanishing cycles and this functor. And so the idea is that our isomorphism depends on the choice of interval. So we can choose in another path from 0 to 1. So it's some element of fundamental group. So from with base point at near 0, we apply this fundamental group and then combine it with our interval. And I want to say that this G gives another isomorphism between these two things, two functors. Which is essentially the same weight. So we can consider some cohomology with support at this line, which is isomorphic to vanishing cycle, and then take the push forward of this. You can write down as a formula. If you imagine that this path is made of rubber, that then you can stretch it in a way that we just go around this point, then it goes this. So you can consider this J as a composition of generators. So for example, if generator is around 0, you use it here, but if you go to 1, you need to add this interval, and this allows you to write down this isomorphism explicitly. And that gives you this formula, where this is Fock's derivative. So it's just direct calculation of this. So you can think about that. Yeah.
So what is Fock's derivative?
Fock's derivative is just definition. It's yeah, maybe I should write down. It's well, I can write down. It's so it looks like, for example, so this way, du, for example, by x. So I suppose it's x and y, x, y, x, for example.
It's derivative of what? In the free algebra?
It's a free algebra, yes, free algebra. Yeah. So yeah, you just need to derive by it will be y xy plus y. So you look for x. No, maybe not. Maybe. Yeah, sorry. So the rule is you take the derivation by x, and for example f by x, and you cut the rest. In this case, it will be 1 plus xy. So we differentiate by x, and we cut this, and it gives 1. And then the next appearance of x, you derive by x, and so it gives xy. Like this. It's a yes, Fock derivative of free algebras, and it appears in the theory of Alexander polynomials. So this notes like this, but it's in fact this Yeah, it's about homology of free group with coefficients in abilization, something like this. Maybe. But yeah, it's just the direct calculation in this case. So you anytime you when you have this loop, so we have a basis essentially of our financial cycle which corresponds to these intervals with marked by some class in homology. So when you transform it with respect by this rule, every time you have loop around this, you just multiply by this element, and you have loop around one, you add new elements, new summons.
Yeah, I'm asking because you wrote something alien transport with a question mark.
Yeah, that's
and
yeah,
so
yes. The question is the same as what was at talk of Misha Kapranov at this in HS this last summer. Because it sounds very similar. He considered this case of abelian convolution. Yeah, so it's additive convolution, right? Additive convolution. But if we take logarithm, then if we take logarithm, then we have many points which corresponds to pre-image of one, right? And so if we're gonna go from one to one, its formula looks very similar to what happens there. So we need to choose every time how to go around, right?
yeah, but whatever, I mean, he said, or this perverse shift story, when you indeed transport the shift of vanishing cycles from one point to another one, you can do it like in your picture with kind of moving around. That's true. And so you get a group element, and essentially you take just a logarithm. So it's like, like a Stokes automorphism. If you, for example, move your vanishing cycle about singularity of your perverse shift, so then alien derivative, I don't know what is alien transport, but alien derivative, it's essentially
Yeah, but yeah, he called it. I looked this video, and he called it alien transport. Yeah. Also, yeah, I don't know.
Maybe I don't know, because it's our joint project, so I should know
Yeah,
this
you
as
should know.
well. Yeah, so yeah, but anyway, it's sort of a logarithm of some holonomy or monodromy. So it's a very simple thing, and probably here it's have a very concrete form because you're working with configuration of points, so you have free pi1 is a free, essentially free group. Yeah. Okay.
Yeah. Unfortunately, I don't understand totally the motivation and what you said about Stokes matter. I don't understand. Yeah,
yeah, we can talk about that, but
yeah,
let you kind of finish whatever you wanted to say.
Yeah.
Okay.
Yeah. Okay. So the idea is that we have another isomorphism, and yeah. So, which is given by this formula, if you wish, and observe that this guy is they differs by action of some element in this W given by this formula. Yeah. Due to because we have this factors, it means that it lives indeed in W. So okay, so and then the final idea that these two guys are indeed two. So we started with we have category of perverse shapes. We have convolution. We don't have fiber functor. This guy is fiber functor by definition. It's by the very definition. And we have two isomorphisms of this functor with another one. And we can say that both these functors equip with this guy with tensor structure. And the slogan is that if our path G is satisfy pentagon equation, then these two tensor structure and this functor coincide. In other words, this composition is automorphism on the tensor functor. That is, it means that this is group-like element. And again, you can see it from looking at this picture thoroughly. And yeah, I don't know how to say it. Yeah, so it's again, huh? So as I tried to describe previously, you have some compatibilities, which this red line is our G. So and if it's a base pentagon equation, then you have some compatibilities. And this compatibilities essentially says that it's not true exactly, because we have this gamma factor, which is in fact B factor, which corresponds to this line, and the previous shifts over this line, that the previous shifts with abelian monodromy, and then correspond to this corrections, to these gamma factors. Yes, this thing need to be calculated, but I want to the only thing I want to say that this compared to this is the formula from Racinet formalism, and this is the formula from Fock differential calculus, which is called the fundamental formula of Fock's differential calculus. You see that indeed, in Racinet formalism, we need to prove that this is a group-like element, and here also we need to prove that condition that this is group-like element. So this is the same thing. So in fact, in the interasoma approach, as far as I understand, they two functors they have kind of beta and RAM functors, and for so essentially they prove only that Knirk-Zamolodchikov equation satisfy double shaft relations, but and in general they use some gadget that they call fake Hodge structure, and I don't understand what does it mean in fact. So, but yeah, it would be nice to understand how it's connected.
So what's the RAM realization here?
Sorry, I don't understand this yoga of the RAM Betty, especially in this case. So for me,
there should be some demodule or whatever, no?
Yes, but yeah. Sorry, I was trying to understand, but
yeah. Okay, sorry.
Okay, but my approach there is no RAM Betty. It's a purely topological thing. It's no mentioning of any Hodge structure. So they're trying to imitate, like they say about that if you have any abstract. So the point is that we have abstract associated, that is an element which satisfy pentagon equation. Then double shaft relation is true. But they say that we have abstract abstract associator, then we can construct some fake Hodge realization, fake. But I don't. So yeah. I don't understand it, but it would be very interesting to understand what it means, because I found some correspondence with my approach. So, and yes, the very last thing I want to say is that, in fact, we prove that associated relation implies double shaft relations, but in fact we used a weaker thing. What did we use? We used this. So we have this pentagon, and what do we need? If our associator is symmetric, which means this guy, it means that the projection of this pentagon on this affine line on M04 is homotopically trivial. It means that in fact the projection of these three sides is trivial, and this thing says that projection of this path equals is opposite to projection of this path, and that means that you can shrink this pentagonal curve to one fiber, and for example and it gives you element of nearby cycle on, or for example of the convolution. So this kind of homological class which presents some class in the convolution. And if it satisfies pentagon equation, that this loop may be shrinked, and it means that it's zero and it's okay. But in fact, we only need that the homological pentagon equation. So we say that pass satisfy homological pentagon equation if this pentagonal cycle with coefficients in this thing is homologically trivial. And if we take universal local system of this kind, so which is just two pull bets. So this is a universal local system, which so we have this two maps from M05 to M04. Then this condition may be rephrased in this way, which is as observed by Enriques and Furusha, that this condition is equivalent to double shaft relation, which is not surprising due to our. So we see that double shaft relations are equivalent essentially to homological pentagon equation, which says that essentially our pentagon of our thing lives in abelianization, in commutator of some group, which is kernel of this map, of these three maps. And so the question is, so we have associated relation which says that this thing is trivial, and we have double shaft relation which thing that said that this thing is trivial only in abelianization. So my question is how it could be that this thing is not weaker than this one, and maybe there are some intermediate relations between. So, for example, we can ask the condition if this thing lives in double commutator of this group. So, so maybe it's a good question to look for intermediate relations between this one and this one. So you asked about this conjecture. So I don't believe in this conjecture, and I think that there are some. It's possible to find maybe some intermediate relation, although I have no idea how to, for example, to find contradiction of this conjecture. So my personal impression nowadays is that this conjecture of Ihara, Kaneka, Zagier is not true. Yeah, and I mentioned here that this construction reminds Richard Kane construction of Turaev co-bracket, and it was some motivation, first motivation for me for thinking about if you look at the Richard Haynes construction of Turaev co-bracket, it reminds a lot this picture, and I think it's possible to find a direct connection between Turaev co-bracket and co-bracket from the interosomum approach. Okay, that's it. Thank you very much for your attention.
Thank you very much. By the way, what is known about the full group of automorphisms of the fiber functors? So this associator is just one group element, yeah.
Sorry, which functor?
No, I mean you have a tensor Tanakian category constructed by this.
Yes.
When you blah blah blah, and you have a fiber functor which is
essentially a group-like elements of our W algebra, right?
Actually, that's a part which I missed or I confused. The role of this transport algebra. Where is it? Where it appears in?
No, the statement due to the interosoma, I don't know. They say that they can prove it.
Prove what?
Prove that this quotient category is a category of representation of W algebra. But there is a statement for additive convolution, and it's which you know this, I think, this story.
Maybe. And another question, there was this approach by Willwacher to double shuffle relations, if I'm not mistaken, of course, through the graph complex. which kind of a bigger thing. So does it somehow appear in this Tanakian formalism?
No, I trying to understand a lot about her approach, but I don't remember that he thought about double shaft relations. Maybe it would be very interesting.
Approach by who?
Wilwacher.
I read a lot of.
Do you know this, Benjamin?
No, I don't know that he thought about double shuffle. In fact.
Yeah, me either. I think it's.
Yeah, you know, I don't remember seeing it, but I remember Maxim told me that. So maybe somehow it.
No,
yeah.
maybe it's in fact I was thinking about this Alexeyev like approach with like Turaev Kobraki, this Kashevara Vern thing.
Yeah.
I hope that these pictures will help to understand this. But Wilwacher, it's very intriguing. I will be very interested, maybe.
Well, if I remember correctly. Yeah, all right. So more questions. Great questions. It's Q&A time. Yeah.
Okay, so Nikita, so if you can compare what you did with our work with Furusho, so can you say that this is a kind of categorical version of our proof of inclusion, or would you say something like that?
Not categorical. Yeah, I don't know. I think my main contribution in this isomorphism to look at this isomorphism, because I didn't find it neither in the Pearson approach nor in your approach. I believe that it is there, but it's somehow hidden, and I suggest to consider it as the main character. So to think about this isomorphism. So maybe it's a good.
Sorry, when we use this iso, so these objects are both Betty in nature, or one of them is Betty and the other is Durham. So what do you think? What do you say about that?
But unfortunately, yeah.
Which one is maybe which one is the RAM?
I really don't understand this story if Betty and the RAM, and if somebody will explain me what does it mean. The only thing I understand about Betty and the RAM that you have fiber functor. You have finally, if you have mixed host structure, you can take the associated graded object with respect to weight filtration and take not associated graded thing with weight filtration. You give you two fiber functors from mixed host structure to vector spaces. One is called Betty and another. Yes. So this is all I know about Betty and Dura.
That's right. Yes.
Yeah.
And, well, and usually the way you think about Drinfeld associator in general. So
yeah,
hold on, Nikita. Let him say, because I want to hear.
Sorry.
Okay. Benjamin.
Yeah, Benjamin, sorry.
So the usual way to think about the associator is that you have two fiber functors, and you have natural isomorphism between them. So one is Beatty in nature and the other is Durham, and that's how you think about associators in general. So here you have this associator side. That's why my question is, so you think that this is a functor from this perv to vector space probably, and one of them takes f to this phi 1, and the other to the h naught, and so you should think that one of them is a Betty functor, the other should be the Durham functor. So if you want to think that this is indeed the Drinfeld associator.
Yes, yeah. So sorry, I said that I really don't understand what is Betty function and what is Durham, but yeah, let me say how I see it. So you have two functors from which is from sheaves, which is
sorry, Nikita, but maybe maybe you're right. So well, in fact, usually, so you see, you really think that you have two categories from the starting point. So starting from the starting point is that first of all, this thing perv, it's already Betty in itself, and so there should be some Durham version of this category of D module, and that's already there. So I'm a bit surprised that you build up so what you call the associator just in Durham terms. So I'm a bit surprised. So.
Yeah, I was spent quite a lot of time to understand it in this way, but finally I have a little bit different point of view.
It's like when you go up before in your lecture when you say, write all this capital phi of x blah blah x23 and so on. So it seems to me that these x23 elements they are Durham in nature, actually.
Yeah, okay, so let me say. The point of view that you have.
Nikita, so my question, so could you do a similar proof of inclusion of just a description of the GT group in the same terms?
Yes, that's a good question. Yeah.
So inclusion in what?
Grothendieck Müller is the whole thing.
So the thing which acts on associators.
Yeah.
The GT group. So it would be a purely Betty object acting on this kind of isomorphisms. So it should be probably an automorphism of this one of these functors, probably one of them. So and then you could describe the Betty group. You see? Well,
sorry, I have an impression that you asked many questions, and it's
just one of them.
In fact, I'm absolutely. But let me make just one comment. Maybe it's I think it's pretty different what you're asking, but nevertheless. So my point of view that I suggest to call this isomorphism Drinfeld associator. Sorry.
Okay, so if so.
What do I mean? I mean that suppose you have, but first thing you have a variation of mixed Hodge structure over here. Yeah, so it's a nilpotent variation which is built of Tate things. Then you have two functors. First functor is vanishing cycles, which is it has Hodge structure, mixed Hodge structure, and this guy is also in fact has mixed Hodge structure due to I don't know theory of Hodge models or whatever. And then you have this isomorphism, and this isomorphism does not respect Hodge structure. This is the point. And it respects weight structure, but doesn't respect Hodge structure. So you.
Sorry. This iso comes from where?
It is absolutely topological thing. It comes from this construction. It's topological. You can shrink your cohomology on.
Okay, but it's not that you are integrating differential forms. There is no integration there, and so.
Yeah. Yes.
No, the only thing you have this variation of Hodge structure. You have a D module, but.
Yes. I suggest to forget about it's another story.
It's a different construction.
Yes. I suggest a little bit different point of view on all this.
But is it good to call it Drinfeld associator because Drinfeld associator usually has to do with integrating integration periods and so on. So here you don't have that. So is it good to call it this way? So.
No, but I explained here. It's holonomy. It's somehow hidden in this isomorphism.
It satisfies the pentagon relation. Yes, so it gives pentagon.
So for I, it satisfies. Yes, if you take I, if you take this specific isomorphism, but the idea is that if you choose, yes, if you choose, this is what I said.
Yes, it's a bit hybrid, I would say. So it's
from my point of view, it's maybe like you have you have the category of mixed Hodge Tate structures over pi1 without 3 points, which is a singularity of 2 points, and you have push forward functor to mixed Hodge structure over point. And somehow this isomorphism encodes this data of this direct images. So it's I can
Okay.
So it's I don't mention anything about fundamental group, and it's
again, sorry, this is Drinfeld associator, so it's just one isomorphism, one natural isomorphism, and there is no more.
Yeah, but by the way, you see that we have isomorphisms from fiber here to fiber here in 2 steps. Like you go there and then it goes here, right? It's like this thing is like sections of your vector bundle, but over an interval.
Yeah.
Not only point, so over all points. So we have, and this construction reminds me of the definition of Drinfeld associator, which is product of two G0 and G1.
Sort of a bit, you'd look at one point asymptotics at the other one, something like that.
Yes. Yeah, and yeah. So sorry, and I asked about your paper. So yeah, I know. Yeah. So my aim was to geometrize this story. Yeah.
No.
I don't think that I invented something new, which, rather than it contains in your texts. But I want to try to understand the geometry behind this. And yeah.
Well, to make the relation with our text precise is definitely not done actually. So no, it's really interesting. So if it can be done at all, so.
Well, I believe why not? I think it's very geometric.
Yeah, so one has to think. No, because really we think in this way of 2 worlds and so on. And here it seems that in the same world you have the 2. So one has to think. So it's talking. So.
Yeah, and I'm very happy with this interpretation of your.
You could do all the same story with the modules, I guess, other than parallel yes.
Yeah, but it makes no difference if you have no Hodge structure. I mean, this. Yeah, I thought, but this category that they are absolutely isomorphic, so it's no matter. This is the point.
I see.
Yeah. Yes. No.
Okay.
Riemann-Giebel corresponds.
Yeah.
So it's a delicate question. So let me not.
I don't know, but if somebody.
It's the point that this thing that you call very standard Riemann-Giebel blah blah blah. This is the essence of associators actually. So
yeah, it's KZ versus monodromy. Yeah.
So yeah. So we need to think.
I don't know.
So okay, thank you. It at least clarifies your work, but I need to think more. So definitely.
Okay. Okay. Any more questions? Well, if not, Nikita, thank you very much.
Thank you very much for your attention.
Inspiring talk.
Thank you.
Too many questions. All right. Yeah. All right.
So long.
Yeah.
So.
Yeah. Okay, great. So thank you. And this is it for today.
Yeah. Thank you.